Okay, we are in section 15.3. We're talking about the physical interpretation of the generating function for the Legendre polynomials. Now, it is a continuation from the last section that we talk about Legendre series, which is one way to express the solutions for the Laplace equation or Poisson equation. In one situation, you get the Poisson equation is the electrostatic problem. And so we are considering a simple electrostatic problem, the electric potential coming from a point charge. So the situation is like that. We have a point charge of charge Q at this location we call R2, and we try to find the electric potential at the location R, which we'll later call R1. So we choose a coordinate system such that the charge is on the z-axis, and the choice of the location of the charge is not right on the origin, but that's for a reason. The angle between R1 and R2 is the usual spherical angle theta. Okay, and now the distance, the length of R2 we call A, the length of R is simply R. Okay, and by this electrostatic problem, we'll talk about the physical interpretation of the generating function, which I copy in here. So this is a generating function which expressed is in a sum of all the Legendre polynomial from 0 to infinity multiplied by h to the power L. Okay, now the Poisson equation is like this. So the electric potential is psi, and the charge density is given by Q and the delta function R minus R2. And now the solution for this problem is well known. You know that the solution is the Coulomb potential, which is proportional to the inverse distance from the observation point to the charge. Basically, is the length of the vector R minus R2. So we can write right away. So psi R is given by just the constant in front divided by 4 pi epsilon 0, and the distance R minus R sub 2. Okay, so this distance. And then we can use the cosine theorem to express that into a function R, A, and theta, which is now Q over 4 pi epsilon 0. So that this distance is R squared plus A squared minus 2RA cosine theta, and square root. Okay, now this is similar to this form, except that there's a 1 here, so we need to pull out either R or A out. Now that depends on whether R is greater than A or smaller than A, because in the generating function, this H value, because we need to take a series expansion in terms of H, we require H to be less than 1. So now we separate into two cases. One is R greater than A. In that case, we pull out an R squared out of the square root. So we can write like Q over 4 pi epsilon 0, pull the R squared out, becomes R, and then this is 1 minus 2 cosine theta times A over R, and then plus A over R square root here. Okay, so that's of a form similar to this one. So compare this with that, you know the H will be A over R, and X will be cosine theta as usual. So this we can write in terms of I should have kept the constant in front. So you have summation L from 0 to infinity PL cosine theta and A over R to the L power, and the constant in front 4 pi epsilon 0 R. Okay, so the total R dependence, you have 1 over R to the power L and 1 over R, so total is 1 over R to the L plus 1 power. Okay, this is for the case R greater than A. Okay, so, and for the other case, R less than A, it's the same thing, except that now we are pulling out A squared out instead of R squared. So now you have 1 minus 2 cosine theta. Instead of A over R, you have R over A plus R over A squared to 1/2 power. Okay, so now compare this with the generating function. So we have sum over L from 0 to infinity PL cosine theta R over A to the L power. Okay, so this is for the case R less than A. Okay, so this covers both cases, and we can obviously, when R equals to A, the two series is the same. Okay, and now this is a special situation where we know how to solve the point charge problem, but we mentioned in the discussion in the partial differential equation chapter about the Poisson equation or Laplace equation. When we solve the Green function, basically solving Green function is exactly like solving a point charge problem. So, and we mentioned that the Green function for the Poisson equation is simply 1 over R1, the distance R1 by to R2. So, and so the Green function is proportional to 1 over R1 minus R2. So now, using these two results, we have an expression for this Green function. Now we can write like using the length of R1 and R2 and an angle between them. Now, comparing these two cases, we notice that the power, the expansion power, is always less than 1. Always if the smaller value divided by a larger value, this A less than R, or the smaller value divided by the larger value when R is less than A. Okay, and then pull out the larger value in front. Okay, so comparing with this situation, we can write this in terms of a symbol R greater and sum over L from 0 to infinity PL cosine theta. Theta is the angle between R1 and R2. And then we have the expansion power R smaller divided by R greater to the power of L. Okay, so the greater and smaller notation is just to indicate that, so if R smaller would be equals to, so R1 or the length of R1 or R2, if R1 is less than R2, and if R1 is greater than R2, if R2 is less than R1, R smaller will be this one, and similarly the R greater will be R1 and R2 in this situation. Okay, so this would be a useful form for the expansion of the Green function of a Poisson equation in 3 dimensions in terms of Legendre polynomial. Okay, and Your textbook continued this section with some discussion on multiple expansion, electric multiples, which we'll skip over because in the EM class you will learn a more general method to talk about electric multiples. So we'll stop the discussion here.